Hey there, my name is Domingues, and this is one of the lab things for magnetic theories. So, first of all, this lab is just an observation between two differing models for calculation of the state adaptation very fun through a tube of Faraday's material. This lab would not be possible without Faraday's law of magnetic flux and magnetic dipole force equation series, right? So Faraday's law is that top one, and it relates electric flux to area electric field as well as magnetic flux to EMFs in a tube. The resulting fields and FM currents generated can then be used in exponential equations of magnetic flux, as well as the dipole field for magnetic dipole moments of like bar magnet, like thanks to the words of Art law and deductions from said law. So what's happening in a physical experiment? The first one is we drop a strong bar magnet, which we previously calculated the dipole moment for in lab 4. Drop it down a tube of ferrous material before the time it took to get out the other end. The average time was, or for our 5 barrels, was 0.9 meters per second. Then we basically will copy the same exact situation using flow script to make it ideal. So here's what the code looks like when you run it. As you can see, that time is a little off. So how to make this model? First, I set up some conditions for the code. Then I define a function for the dipole B field, just using the equation right there, which I showed earlier. The dB/dt, which is the EMF, which will be induced inside of each infinitesimally small ring throughout the tube itself, and then calculate the EMF or the current through that. Then we can set up a loop for the magnet falling through, if it's in or if it's not, and sending gravity on it there in that picture as well. And then we can calculate the rings and B field and ring by making an equation. So, lab questions here. The intensity of the coloring on the tube indicates the magnitude of the following of the current flowing through each ring. Red will indicate the current in opposite directions. Which color corresponds to clockwise, which one to counterclockwise. So north facing down, clockwise current is formed, and we know that if we're looking at it from above, we should see a counterclockwise current. And I think that was red. I think red was the counterclockwise current, which would be seeing the ring from above. What happens to the dynamics of the system when you flip the magnet around? The direction of the currents in the ring above below switch. So we have counterclockwise, or sorry, if we had counterclockwise above before, we did not see clockwise. So next question. In the tube of the real world system compared to that of the computational system, how might the computational system be made more accurate? Our experimental magnetic dipole was probably a huge source of error because it was highly incorrect. If we obtained a guaranteed value for this, it would probably be much more accurate. So that would obtain a guaranteed value, or just a way to calculate the true value of our magnetic field. What does the shape of our velocity versus time graph tell us about the forces in the magnet? So this is a huge part of the lab, understanding that we can set sort of a terminal velocity, because we see that our velocity is falling will become constant. That means that we have no acceleration due to forces. That means if some forces is zero, that means that our gravity and our towards left. So the system in this experiment is just the bar magnet, and our surroundings are everything. So the aluminum foil that we use, as well as the gravity that's acting. So the fall time for using the lab for calculated magnetic dipole is 67 seconds. So that's probably a very big source of error, or that means that our lab 4 was very wrong. A magnetic dipole that would match our average that we saw in the experiment would be 4.350 joules per Tesla. And then the calculation for the dipole moment, the main source of error, is there could be other things. We could have also messed up the timing, but this we could have dropped it with different initial velocities, but this is obviously not as severe at 67 seconds. So what if the resistivity on the conductor was 0? When we find the EMF, we can see that we're just setting I equals EMF over R. So if that R approaches 0, then it would mean a higher current. Infinite current means infinite. Then it would make the magnet go slower than the tube, even slower than it is already. So if we cut holes or slots in it, it would make our magnet fall faster, because those currents would be broken, and that would decrease the magnetic field created by the induced EMF. That's all. Thank you.